Welcome back. The next video in our sequence for the study of reinforced concrete design has to do with the fundamental behavior assumptions of the beams in general. And a lot of this will be some mechanics and materials review. In the previous videos, we've kind of focused on some of the assumptions associated with the material specifically, focusing on concrete characteristics and the steel characteristics. But in this, now we're going to start kind of looking at some mechanical based assumptions that we're going to be looking at, and that's the purpose of this video. We'll do a little bit with the transform section, kind of revisit some basic mechanics calculations, and then we'll kind of define some of the terminology that you'll hear, in your studies or even out in the workforce as you start to look at it. So this purpose is to talk about the fundamental behavior assumptions. All right, so what I've done is I've kind of made a list of some of them, and we'll kind of talk about these, and we'll run through these fairly quickly. Okay, I've got, the first one is that all internal forces, whether it's the normal, the shear, the moment, or the torque, are always in equilibrium with the applied loads. Okay, so this balances our internal stuff with our external stuff. Okay, and this basically mandates an assumption that of what I affectionately call the mantra of structural analysis. Okay, and I use an acronym of LEIH, where this defines the characteristic properties of being linear, elastic, isotropic, and homogeneous. Now, if you remember from mechanics, if I plot load versus deflection, linear means that for 100, there's a linear relationship that exists between those two. So if I have a 100-pound load that gives me a certain deflection, if I double the load, I double the deflection, that this is a straight line. That's the linear portion of it. It has to do with load deformation response. Okay, some structures, for a lot of structures, that's typically the case. Things like beams, that will work. But if you get into systems like cable structures, this may or may not be the truth. Okay, so we got to be kind of careful on limiting what we're looking at. Okay, the elastic portion of this, okay, is basically the relationship that exists between stress and strain. So remember, we said that for most stress-strain characteristics, and for mild steel, it was kind of a picture that looked something like that you hit this peak point, and then it started to do something a little bit different. Elastic was everything up to that proportional limit and less. Okay, so it's the region that is basically a linear function on stress and strain, because remember that the slope of that line was E, or Young's modulus. So that's the elastic portion that we're not going beyond this point, because that's where things start to get a little weird. Okay, we get into some nonlinear behavior, some plastic behavior, and then this topic becomes a whole lot more complex to work with. So we're going to kind of limit ourselves to staying where we know how things are behaving. Okay, isotropic and homogeneous have to do with the distribution of properties in given directions or even throughout a given cross-section. By nature, concrete is neither one of these, but we're going to make an assumption that it's close enough so that we'll be allowed to stick with our assumption here. Okay, because again, concrete is a combination of, cement and water and sand and really big aggregate particles, so there's no uniformity of anything. So it's, on a micro scale, it's not homogeneous. Now, maybe on a macro scale, it could be fairly considered homogeneous, but we're not going to start splitting those hairs at this time. So we're going to basically kind of wink and nod at these, say, yes, you guys are factors, but for all the problems we're going to look at, that's not going to be a concern for us. So, all right, but just as long as we're aware of it. Okay, the next one is a big one, okay, and that is that the strain in the embedded rebar has the exact same strain value as the concrete around it. So if you remember, we talked about the rebar having these deformities that exist, and I pour my concrete around it. What we don't want to have happen is to have the concrete move relative to the steel. So if the concrete grows in length, the steel grows in length by the same amount. Now, we saw that with the shrinkage calculations in the last video, that's not always the case, but they're close enough in magnitude that we don't ignore it. Because if this guy moves too much relative to this, I can destroy the bond that creates the interface. And that interface is what allows me to transfer stresses from concrete into steel and to use the steel as a tension element to help with the compressive side of things in the concrete. All right. So basically, by saying that these two have the same strain in it means that there's no relative slip on there. And so that there's no microfracture occurring or any sort of other issue that occurs at the concrete steel bond interface. So that's kind of what we're looking at. Again, we'll talk more about this when we get to bonding and developmental length. Okay. The next one is a mechanical assumption. Okay, and it's the old familiar plane sections remain plane. Okay, so the idea is that if I take a beam and I were to draw a straight line on this thing, that represents the cross section, and I allow the beam to deform in its deformed shape, that line remains straight. I don't get any sort of warping or any sort of strange behavior. Now it's allowed to rotate. You notice that here it was vertical and now here it's slightly inclined, but it's still straight. Okay, and what that does is that basically says that the strains along this line are predictable, that they're related to each other in a linear fashion. And we'll talk more about that as well. But that's the plane sections remain planar after loading. Okay, all right. Our fourth one has to do with, in most cases, concrete is assumed to not be capable of resisting tension. And, if we do kind of some quick calculations of this, if you remember, for an F prime C of 4,000 PSI, the tensile stress limit for direct uniaxial tension, we said, was 4 root F prime C. We said that in a couple of videos past. So if I run this calculation out, you can see that the limiting stress on this is 253 PSI, and that's in tension. So I'll put a T on the end of that guy. All right. Now, if you look at that, compared to the compressive limit, which was this guy, I'll put a C on him. Okay, 4,000 PSI in compression, I can only get 253 PSI in tension. That accounts to about 6%. Okay, so it's not a big contribution anyway. And so for the sake of simplifying our calculations, for F prime C of 4,000, we're just going to neglect the tensile side of things. Okay, and that will make our calculations so much simpler and so much more straightforward. And I'm only giving up a minute amount of the actual capacity of the concrete. And it's worth the trade-off, believe me. Okay, all right. The next one then is that to model concrete, computer modeling, the modeling of concrete is significantly more complex than steel. And again, part of that comes back to how do you model bond? How do you model the different particle sizes and the stresses and strains that each of those particles wants to take? Okay. Now, what we do to kind of cheat our way around this is we made that LEIH assumption early on. Okay. And, again, we're going to kind of wink and nod and say, yeah, it's not 100% accurate, but realistically, concrete is neither I nor H in that. And even seldom E. Once you crack, it's not behaving the same as when it did when it was uncracked. Okay. And so those are some of our primary assumptions that we're looking at for concrete. So we need to kind of keep those in the back of our mind. The biggest ones that we have is we're going to neglect the tension, and we're going to assume that there's no slip that occurs between the rebar and the concrete. All right, so let's start kind of talking about axial loaded members and kind of how we can start to do some stress strain calculations on this. Okay, so as a reminder, we're going to say that Hooke's law is just sigma equals E times epsilon. That's the one uniaxial Hooke's law, not the generalized three-dimensional, although three-dimensional would kind of follow some of these relationships to a degree. We're going to just kind of play off of this uniaxial version. Okay, we're going to deal with elastic theory. So that's the E in our LEIH assumption. So we're sticking to that. And so we know that the strain, in this case, we're looking at the concrete strains. The strain in concrete is equal to the stress in the concrete divided by Young's modulus. Okay, and we know that the strain in steel is equal to the stress in steel divided by E sub S. Okay, and again, this guy was 29,000 KSI. That's the stress in the steel. Okay, so if we assume that our second assumption was true, and that was the one, if you look back on this, was that the strain in the embedded rebar is the same as the concrete around it. Okay, this was the no slip criteria. Then whatever strain occurs in this bar is matched by a strain in the concrete directly next to it. Okay, and so if that's true, then the strain in the concrete is equal to the strain in the steel, says that the ratio of those two stresses have to also be equal. Okay, and so what I can do then is I can say that the stress in the steel then is equal to the ratio of Young's modulus for steel to Young's modulus for concrete multiplied by the current stress state in the concrete. Okay, and if you remember when we did transform sections back in mechanics and materials, we said that this ES over EC was a constant that we called as N. Okay. Now, just to give you kind of a sense of the magnitude of the values of this, if I plug in this for 4,000 PSI concrete, we said we could calculate Young's modulus for concrete as being 57 square root of F prime C. Okay, now again, this gets us a KSI unit. Remember the formula I showed you last time, this was 57,000 square root F prime C. But what that did is that got me to PSI. Okay, so you got to kind of watch the units. Again, the F prime C inside the radical, though, has to be a PSI value. Otherwise, the math doesn't work. But it's the PSI and KSI come off of this. Okay, so for 4,000 PSI concrete, we have an EC that is 3,604 KSI. So we can calculate N for this grade of concrete then as being my 29,000, which was the steel Young's modulus, divided by what I'm calling is 3,600. I mean, I'll give up 4 PSI, right? 4 KSI, it's not much. Okay, and this is approximately 8.0. So there's an 8.0 difference factor between the stress in the concrete and the stress in the steel. Okay, so let's go through and let's see what we can kind of start to figure out about a general cross section. Okay, we're going to look at a rectangular cross section. Okay, and we'll be doing a lot of these over the next couple of lectures. We're going to say that if the rectangular section has a width of B, it has a height of H, and then we're going to say that all of these reinforcing bars that cut through this, that we have 6 reinforcing bars that we're going to call as area of steel, AST. All right, so a couple of calculations we can do. I can do the gross area. Okay, so that's the gross area. Okay, of this would be B times H. Okay, and we know that that total area comprises the concrete area plus the steel area. Okay, so if I rearrange this, I can say that the concrete area, which is the part excluding the rebar, is equal to the area gross minus the area of steel. Okay, so what we can do then is we can then use a transformed section to start to figure out equivalence. Okay, because what I can't do, our mechanics formulas have problems dealing with sections of 2 materials. I have to convert one material into another. Okay, and so what we're going to do is we're going to use that N characteristic that we had to change the area of our cross section of 2 materials into an equivalent section of 1 material. And once I do that, then I can do my calculations. All right, so what we're going to do is we're going to kind of play with this a little bit. So in effect, I'm going to take my steel area and turn it into an equivalent concrete amount, and then be able to calculate our section properties and be able to do some stress calculations off of that. All right, so we're going to say that the area total is equal to the area of concrete plus N times the area of steel. This is an equivalent concrete area. All right, and so we'll play with that guy. Okay, and so when I look at this, then I can come in and say that the total area of the concrete then we said would be equal to this formula, our area of concrete that we had being A gross minus area of steel plus N times the area of steel. And so I can calculate very quickly the equivalent total area of concrete as being the gross area plus this N minus 1 times the area of steel, because I've got a positive N here and I'm making 1 away here. Okay, and so that becomes our equivalent concrete area as a transformed section. And you'll know all of these parts. I know the rebar that I have, I know my gross area, and then of course I know the ratios of their Young's modulus for that N factor, and we should be good to go there. Okay, so that's kind of how we're going to kind of handle transformed sections. We'll come back around to this here in a second. All right, so let's talk a little bit about some calculations we can do with axial compression. Okay, axial compression is basically where steel and concrete are both resisting compressive loads. Okay, so maybe I have, some sort of column without bending, and these were my 3 rebar on there. If I load the end of this column, everything is in compression. Okay, and so we can say then that the axial load, the nominal load Pn, is going to be equal to the stress in the concrete multiplied by the area, the total area that's been transformed to concrete, this ATC value that we had up in this equation here. All right, so if I do a little bit of algebra, I can get FC multiplied then by these areas will get me the load that can be carried for a uniaxial compression case. Okay, so in compression, both the concrete and the steel are working. In axial tension, though, remember we made the assumption that there's no tension in concrete, okay, that the steel does all of the work. So that was our assumption number 4. So only steel is resisting the tension. So if I take my same formula, which was my FC times my AC plus my FS times my AST, basically that first term becomes 0 because I'm not allowed to have any tension in concrete. And so we'll say that the nominal tensile capacity of a section is directly related to the stress in the steel multiplied by the area in the steel. Okay? So if we go one step further and we say, well, let's take Fs to its limit, which we said was going to be Fy, because again, we're neglecting the strain hardening region on this, then the nominal load, axial load, is going to be equal to Fy times AST. This is the maximum nominal uniaxial tensile load. Okay, I can't go any more than that, or else we're going to be well beyond that. Okay, now, just to kind of give you a sense of some values, of one value that we're going to use fairly often is we're going to calculate the yield strain. That's Fy divided by ES. That's 60 KSI over 29,000 KSI, just a straight Hooke's Law calculation. And so for 60 KSI steel, the yield strain is assumed to be 0.00207. And I flag this because you're going to use this guy over and over and over when we start doing our analysis, all right? Okay, all right, so we're going to use that a whole lot. Okay, all right. So now, let's talk a little bit about, so that was our uniaxial case. Let's talk about our flexural cases. Okay, and so we've got a couple of things that will happen here. Okay, for uncracked concrete, the flexural behavior, this kind of harkens back to our bending of homogeneous beams. This is the H in LEIH. Okay, and you can see why we need all those assumptions, is that if I have a cross-section that's subjected to shear and is subjected to moment, okay, if you remember, sigma was equal to minus my over I, which meant that I had, for a simply supported situation, a negative at the top, a positive at the bottom, and it was a linear variation in between. Because m was the moment on the section, I is the moment of inertia of the cross-section, and y was measured from the neutral axis. Now, if you remember, we define the neutral axis as being the location of zero strain. So if I'm at zero strain here, then my neutral axis comes across, and we know that Hooke's law says that sigma is equal to E epsilon. If we're uncracked, we're still in that linear range, that the stress at the neutral axis is also assumed to be zero because epsilon is zero. So we'll take advantage of that as well. Okay, so, and again, for beams, one thing that we want to point out then is that we're going to neglect axial loads in beams, okay, generally because of this LEIH idea that the strains that will come as a result of the moment are going to be so much more significant than the strains that come out of a normal axial loaded flexural member. Okay. Now, what you notice in these stress diagrams, and we need to get in the habit of drawing these every single time, especially this guy, because this is going to lead us to our Whitney block when we get there, how we can start to analyze this basic bending stress behavior, that the bending stress is maximum at the outermost fibers of the beam of the cross section. So you can see that it was highest at the bottom and highest at the top. For a rectangular section, their magnitudes are the same. So for a section that looks something kind of like that, that would be our stress and our strain associated with that. That the stress at the bottom of the beam in an uncracked section is the same as the stress in the top. Okay. Now for other shapes, T-beams and L-beams and those kind of things, that may or may not be the case. But for rectangles, which is where we're going to start, that will always be the case. Okay. All right. So that's how our flexural stresses work. Stresses due to the moment. Okay. On the same section, I also have my shear strength. Okay, or my shear stresses. And if you remember, for a rectangular cross-section, again, same section, moment, and shear applied, the shear stress indicated by this tau symbol, where the neutral axis was at this location, that was the location of tau max. Okay, and we can look at that from our mechanics formulas. If you remember, tau is equal to VQ over IT. And Q is yet another section property, is the first moment of area about the neutral axis. Okay, and it takes on its maximum value at this location. Remember to calculate Q, what you're doing is, say this is my neutral axis or my centroid. To calculate Q, you are taking the area either above or below that line and multiplying it by its distance down to that line from the centroid of the area that you're looking at. Okay, and so again, we'll cover this a little bit later, but if not, grab a mechanics book and they'll be able to walk you back through that. But that's kind of the basics of what this section property is. This isn't a real friendly formula to work with in engineering. I mean, it's a necessary evil, and we'll do some things that kind of cheat this a little, and we'll be dealing with maybe a tau average, which instead is more of a V over A kind of calculation, is not uncommon. Okay, but for now, just to kind of be pure to the theory, this is the way it should be done. Okay, so what you see then is that the shear stress occurs as a maximum at the neutral axis location. Now compare that back to what you saw for the flexural stresses. The neutral axis was here at this location. So what's good about this is that the shear location of maximum stress is a different point in the cross section than the flexural stress. So we don't get a whole lot of combining of the two effects together. You do get a little bit, but for most purposes, they're pretty much independent. So what I can do is I can design the stirrups to pick up the maximum shear stress, a set of steel that runs vertically in this direction, to pick up this guy, and it will be completely unaffected by any longitudinal steel that I put in the beam this way in order to pick up the normal stresses. Okay, and so that's kind of a handy little trick that will happen from time to time. Okay, all right, so that will kind of get us kind of through our basic process. I'm going to show you kind of the way this class is kind of laid out as we start to look at these, okay? And as we go through the class, we're going to have a series of, calculation sheets, kind of almost like worksheets, and this will be part of your homework assignments as we've talked about, outside of the nature of these lectures. But what I've done in all these, and I'll kind of show you these pictures for you. We may not work through them all the time, but just to kind of walk you through, this will kind of, if you were able to answer these questions, this becomes like a flow chart or a progression through an analysis problem. So what I have in this example is I have a 28-day compressive strength of 4 KSI. I have a yield strength of reinforcing of 40 KSI. And we want to find the uniaxial capacity using transform sections. All right. So all you're going to do to be able to do this calculation, I need to know what ES is. You know that value. You need to compute EC, and then you need to compute N. For our beam, we have basically an 18 by 18 square or rectangular section, and we've put steel consisting of 12 number 9 bars all the way around this thing. Okay, so I've got 4 in this face, 4 in this face, 2 in the middle at the top, 2 in the middle at the bottom. Okay, and with that, I've got everything that I need to know using the information in this packet to be able to proceed through this set of calculations. So again, that's kind of the way we're going to do it. Obviously, this is a fairly simple one, and so I'll leave that as kind of the first exercise for you. And then I'll post the solutions where you guys can see them on our class website for those of you that are taking this as part of our concrete class at our university. But for those of you that are here along for the ride, use these kind of as a template to be able to solve for all of those. Okay? All right. Anyway, we will stop there. That's our kind of our introduction to some very, very simple calculations, mostly kind of talking about stresses and transform sections and so forth and so on. It's very straightforward at this point. It does get more difficult. So thank you for tuning in. As always, if you'll leave a comment for us, let us know what we can do to make things better for you. And as always, like and subscribe to the channel. And we will see you next time. Happy engineering.